Hey guys, this is James. Thanks for tuning in to our revision 2019. There is actually 2.5 hours of content all about the A-Level P Biomechanics course, which is assessed as part of the physiological component. The notes pages which you need to follow along with are just down in the description. There are a couple of other links as well. And if you don't want to take this as a full 2.5 hours of teaching, which many of you won't, there's lots of little links that will jump from one part of the content to another. So have a look in the description below. That's going to help you a great deal, okay? So with that in mind, let's crack on.
So Newton's laws, and I think it's one of those subjects or topic areas which is kind of taught in a shaky way sometimes. So let's make sure that we simplify this and clarify this and understand this in the way that we need to do. So look, I guess for me, we are going to look today at definitions and what these laws actually are, but more importantly, we're going to look at application. Okay, so for me, this is all about the application of these ideas so that you guys can effectively apply them in literally any direction you need to. One of the things I think we need to draw out first of all is to clearly understand that Newton's laws describe how all motion occurs. Okay, so one type of motion, for example, let me write this in. So we're describing a notion of all motion, a notion of all motion. I might use that. It's a little catchphrase. We're describing all motion. And of course, one subpart of motion is something like stillness. You might think, what? Well, that's not moving. Well, exactly. So we need to be able to explain all movement and non-movement using these three laws. And that ultimately is why it's so pivotally important for us from a sports science or physical education perspective. Because if we're interested in the science of movement, then we have to fundamentally understand the three base principles by which all motion and stillness is characterized. Okay, so that's what we're looking to do today. As you can see from this little illustration here, we need to clearly understand that there are three laws, N1, N2, N3. And I would also strongly encourage you to learn these words related to each one. So N1, Newton's law 1, which we're going to come to in a second, is referred to as the law of inertia. More about that word in a second. N2 is the law of acceleration, and N3 is the law of reaction. I encourage you to ensure that you can reflect and relate these laws using those three words, but because by remembering that law 3 is about reaction, it kind of pretty much gives away what the definition is, which we'll come to in a few moments' time, and then obviously we can begin to look at the application. So these I feel are crucial. I don't know if a mark scheme is going to give you a credit for saying N1 is the law of inertia. It depends on the specific question, I suppose. But by understanding that that's its name and understanding what the concept of inertia is, which we're going to come to right now, then that's going to make it very, very memorable for us. So this little schematic here is a nice one. Now, let's get on to Newton's first law. So we already know this is N1 because it's the law of inertia. Let's get on to our definition here. An object, sometimes we say a body, will continue in a state of constant velocity until compelled to change by an external force. So it feels wordy. It feels like, what does that actually mean? Well, so effectively what this means is that an object, a sporting object for us, a ball, a body, a person who's running or jumping or whatever, an object will continue in its state of motion, until an external force applies. So constant velocity can kind of mean two things, okay? It can mean the notion of sort of constant speed. Let me change color actually. It could mean something like constant speed. Just literally switching the vector of velocity for the scalar of speed. Or it could mean stillness. And that is where we want to come to this word. Inertia literally means a reluctance to change state. Okay, so let's actually link that off. We've got here inertia is reluctance to change state. Okay, so what we're saying here is that once an object is moving, or indeed when it's still, the tendency is for that object to continue in that rate of movement or that stillness, which of course is also a rate of movement. So let's see if we can apply that. Let me draw some kind of dodgy golf tee here. So I've got a golf tee, really badly drawn, I think we can all agree, but there's my golf tee there. And on the top of this golf tee, I'm going to have a golf ball. Okay, so pretty poorly drawn, but you get the idea. Here's my golf ball, and somewhere here we're going to have some some grass. So I've got my golf ball, which is sitting in this position here. So I think we'd all agree that we would characterize this movement as stillness. Okay, stillness. In other words, it has constant velocity. The sprint on the block remains completely stationary. The golf ball on the tee remains completely stationary until what? Well, it remains completely stationary until it's compelled to change by an external force. Well, in this case, what is the external force going to be? Well, for us, there's going to be some golf which clatters into it. Here, this is a golf club. This is the head of a golf club, by the way. This golf club is going to hit it and contact here, okay? And of course, then we're going to overcome that state of inertia, okay? We're going to overcome that state of inertia. So whatever the contact force is obviously, as we're going to look at the moment, proportionate to the action which is going to occur. But that ball is going to remain stationary, it's going to remain constant velocity, it's going to remain still, it's going to remain in a state of inertia until compelled to change by the external force of a club face contacting the ball. Okay, I suppose you could say a big gust of wind or the tee falls over, but the one we're interested in is the golf club contacting the ball. So that shows us how we've got a state of inertia there. Now, this is just sketching because we're going to put this into much more detail when we look at vertical and horizontal forces. We could even say that, look, there is our weight force, and we're drawing a vector there. There's our weight force. And of course, what we have from here is that we have our reaction force. Our reaction force, we could call it T reaction force from the T, which is equal in size but opposite in direction. These are arrows, by the way. These should be a little clearer here, to be perfectly honest with you. So what do we have there? We have a weight force and a reaction force which are exactly equal, okay? And that means that we can describe that as zero net force. Okay, zero net force. Net simply means total. Okay, so net means total or overall. So on this golf ball right now, there is a zero net force because the net force is the two vertical forces cancelling each other out. So as a result of that, we get a state of inertia, a state of stillness. Once this club head contacts this ball, and this ball goes shooting off through this action force, okay, this action force, then of course we're not going to have zero net force anymore. We're going to have net forward force, which is going to cause that to happen. And of course we're going to get acceleration in that case. In other words, we're overcoming inertia. So what does law 1 tell us? It tells us that an object remains in a state of constant velocity or stillness until an external force compels it to change its state, compels it to accelerate or decelerate. So let's have a look at the second law. We have the law of acceleration. Remember, we have that here, the law of acceleration. What does it tell us? An object will accelerate proportional to the force acting and in the direction of that force. So we have two parts. We have part 1, which is here. An object will accelerate proportional to the force acting. And part 2 is it will accelerate in the direction of that force. So in many ways, this should come across to you as very much common sense. And really where we want to go with this is we want to say that force, this is how we could summarize it, equals mass times acceleration, which of course in most contexts we're going to write as F equals, I can't remember what colours I used, MA. Okay, so why is this important to us in terms of our sort of sporting, and so why is this equation important to us? Well, think through sort of sporting actions, think about runners, think about balls, think about jumps, think about hits. We've got a situation here where we're basically saying the force applied is a product of two things multiplied together, the mass times the acceleration. But of course in sporting contexts, in basic terms, the mass of objects does not change. In other words, the mass is a constant. And if it's a constant that doesn't change, then really what we've got is we've got force equals acceleration. What do we have in this equation here? An object will accelerate proportionate to the force acting. Force equals acceleration. So let's just get to the basic principle here. I'm just going to give you an example of this. Hit it with more force and it will accelerate more. Now, I don't think that's going to shock anybody, right? So if you think about, what should I use as an example? If you think about a table tennis ball, which you strike your first shot with more force and your second shot with less force, which of those examples is the ball going to accelerate more? Well, it's the first one, right? You've applied more force to the ball via the bat, therefore it's going to accelerate to a greater degree. And Newton's second law states that exact principle. Hit it with more force and it will accelerate more. Or we could say apply less force and it will accelerate less. We could say apply more force and it will decelerate faster. Think about catching a ball, for example. We're decelerating the ball. The more force we apply to it, the faster it's going to decelerate, which is why sometimes we cushion the ball to decelerate it slowly, for example. So let me go back to my very, very bad drawing from before. Let's actually go up here. So, of course, if this club face applies a greater force, action force, remember, to this ball, okay, its outgoing velocity is going to be higher. Okay, so its outgoing velocity is going to be higher because more force has been applied to it, and the force applied is proportionate to the acceleration. Okay, so we hit it harder, it travels faster. There's not going to be any great surprises there. Now, the second part of Newton's second law says that the acceleration happens in the direction of that force. So again, if we think about this example here, in which direction is this ball going to accelerate? What does your intuition tell you once we've got our action force here? In which direction is that ball going to accelerate? And you'll probably be able to tell me, well, it's going to accelerate in that direction and it's eventually going to come down somewhere over here, right? And you'd be exactly right. So in this sense, if we hit the ball at that angle, it's going to follow that path. If we hit the ball at that angle, it's going to follow that path. In other words, the ball is going to, in this case, the ball is going to travel in the direction that the force is acting. Okay, the direction that the force is acting. So this has certain applications that we might want to think about this direction point. Well, first of all, we want to give direction, so we want to obviously apply the force in the direction that we want the ball to go, or the jump to take off, or whatever. But we also want to do something like a follow through. And why would we do that? Now, if we talk about impulse now, we'd know that force times time, if we apply the force for longer, we get a greater impulse, but also we get a greater accuracy. Okay, so we get a greater accuracy of direction by applying something like a follow through, because the follow through, of course, acts in the direction of the intended travel. So law of acceleration works in that way. Finally, we have what we call the law of reaction. And I've found in the past that a lot of times students can regurgitate this principle, but they don't necessarily understand this principle. So let's see if we can get both of those things. We're saying for every action, there is an equal and opposite reaction. Don't forget that comma in there, please. It's important because we want to have good grammar. For every action, there is an equal and opposite reaction. Okay, for every action, there is an equal and opposite reaction. So what does that mean in effect? Let me draw my T and my ball in again here. Okay, so pretty ropey drawing. Again, there's my T coming down there. Here's my green grass. And you got me singing there. And here's my golf ball. Okay, drawn even worse than the first time. Here's my golf ball. And what we're saying now is that if our club head, which is here, let me just shade that in, if our club head here, if it applies this action force on the ball, then the ball is also applying an equal and opposite action force on the club head. And by the way, that should have been slightly longer, so they should be the same length. And this would be what we call the reaction force. Okay, so we've got the reaction force there. Okay, so we've effectively got the club applying the same action force to the ball that the ball applies back on the club. And you might want to ask yourself, well, therefore all forces are equal, therefore why does it accelerate off in that direction? And the reason that is of course that this club head has more mass. Okay, it's got more, it has more mass to it, and therefore it has a greater inertia. Okay. Oh, sorry. Let me restate that. It has a greater momentum at the contact point. So in this case, of course, the ball is going to accelerate off and end up over here somewhere. The ball is going to end up over there, traveling on that flight path there. It's going to end up like that because the club head has a greater momentum because it has a larger mass than the ball does. You might want to think, when you press your feet down onto the ground, you take off, right? So if you push downwards, okay, what's ultimately going to happen is the ground is going to push back up on you, and you are going to be the one that accelerates upwards rather than the Earth accelerating downwards. Well, why? Because the Earth has a lot more mass than you or I does. You or I do. So therefore, it's you that accelerates upwards from that collision of your feet with the Earth, rather than the Earth kind of being pushed away. You might also be able to think, if you've ever you could actually try this. If you've got like wheelie chairs in your classroom, or you've got two people on wheelchairs, if you're approximately the same mass and you sit opposite each other nice and close, and you sort of both push each other on the shoulders, you'll notice that both chairs accelerate away from each other. Why? Because both have the same mass. So in this case, for every action there is an equal and opposite reaction. The club face applies a force of 250 newtons on the golf ball. The golf ball applies a reaction force of 250 newtons on the club face, which is equal in size, 250 newtons, but opposite in direction. So if the action force is upwards and forwards, the reaction force is downwards and backwards. In other words, it's equal in size and opposite in direction. In fact, that's a good thing to think about. Equal in size, sometimes we say magnitude, and opposite in direction. So let's actually do some application of this. Let's have a look at a question all the way down here. Let me make that slightly bigger. Hang on a second. Let me make that slightly bigger, a bit like that. So we've got a question here. Select one of the performers below and explain how a knowledge of Newton's laws could help to improve their performance. So we're in the business here of explaining how. So we're going to be using language like by, through, this means. I could use a because in there because I'm explaining how. If you're wondering where this kind of connecting language comes from, go and have a look at our roadmap service. It's completely free. It's on our website, theeverlearn.com. Go and have a look. It's going to make a big difference to you. So let's have a look here. We have got our first part of our answer. Let's put it in. Laura, so I've chosen the gymnast here. Laura could use N1, so I'm looking at the law of inertia, by, now I'm explaining how, achieving a state of inertia when balancing. So I'm going to get my mark for saying a state of inertia. That's going to help her when balancing. And she's going to do this by having zero net force, which causes stillness or constant velocity. So I've taken my key language all the way up here from N1. Okay, I've got my language of, inertia, zero net force in this example, and I'm putting it into my answer. So what does Laura therefore want to do? She wants to achieve zero net force to get a perfect balance in a handstand or a headstand or whatever. Zero net force. Remember, I'm talking about a rhythmic gymnast here, not just this particular image, which causes stillness or constant velocity. Now, we've got a 6-mark question here. We're probably going to get a sub-max of 2 for each of the laws because we have to apply all of Newton's laws and knowledge of Newton's laws, all 3. So Laura could use the law of inertia by achieving a state of inertia when balancing by having zero net force, which causes stillness. I'm explaining how, I'm using my key language, I'm applying it to the performer. Next example. Use N2 by, again I'm using my by language, by applying a greater force to the ground when leaping. So of course if we get a greater force, what's that going to mean for our upwards acceleration? This means a greater height as acceleration is proportionate to force applied. So in other words, we're saying push harder and you accelerate more in your jump. Okay, That's what we're talking about. I could go on and talk about direction. Push directly downwards, and Laura would travel directly upwards. Okay, because that is the reaction force is the one causing her to go up. So therefore, we could talk about the directional aspect of that as well. And my last point, which I really struggled to fit in, you'll see in a second. What have I done? Bear with me a second, folks. My last point. So let me just go across. You see here, I really struggled to fit this in. So use Newton's law 3 and 3 by applying the right amount of force to the ground at landing. Okay, so the right amount of force to the ground at landing. So the ground applies an equal and opposite force on the gymnast to bring them to a stop. Okay, so what am I saying here? So when she lands from her jump, for example, we're saying she has to apply the right amount of force to the ground so the ground decelerates her appropriately. She also has to do that in the particular direction. Okay, she's going to apply the force downwards so the ground applies a force upwards on her and prevents her from hitting and colliding with the floor. That is an excellent example of what we would describe as application of these rules, and we've done that with the gymnast. Here now we're going to have a look at how we do this with a goal defence netball, and actually I'm going to leave you to complete the answer. All I'm going to do here is plan it for you, okay? And I'd encourage you to try and get your 6 marks out of actually putting this in. Julie sometimes plays as a goal defence netball. Apply all of Newton's 3 laws to the performance of rebounding, jumping to catch a missed shot in netball. So let's see what we would have. So I'm going to do my N1. Here's my little plan for how I'd apply it to netball. She's going to overcome inertia with a large force. So actually in this example, I'm not saying she's still. I mean, I guess you could say she gets into the ready position and holds stillness. You could do that, I suppose. But I'm saying here, she overcomes inertia with a large force. So I'm using Newton's first law, but I'm actually saying how she'd overcome that first law. And I'd also say that the external force is the ground reaction force. So when she's jumping, of course, so if we think about, let me do some rudimentary drawing of a netball player. Oh my God, this is going to be disastrous. So here's my netball player about to take off. Ball's up here somewhere. Okay, of course, what have we got here? Well, we've got weight force, which is acting downwards. There's my weight force. And I've got ground reaction force acting from both feet. Ground reaction force. So of course, if our ground reaction forces together are greater than our weight force, we're going to get a direction of movement upwards. Okay, so we're showing that here. So the external force is the ground reaction force. So we want to be able to define that term. Next, let's have a look. Newton's second law. The more force she applies, the greater the height. We looked at that with Laura as well. We can define this with force equals ma. Force equals mass times acceleration. Julie's mass is constant, so the more force she applies, the more she'll accelerate. And the force is upwards. So as we said a moment ago, the force direction is upwards, and we already know that that's from the ground reaction force. Now M3, apply more force down to get equal and opposite force up. So the harder she pushes downwards, the more force she's going to get upwards. Okay, so that's equal and opposite force up. And apply force in accurate direction. In other words, we're saying here we must state the direction. So apply the force downwards so that she gets the reaction force, ground reaction force, upwards. And I would really encourage you guys to have a go at actually writing that answer in. Now, look, you guys have to put that into a flowing structured answer. But if you look at my answer up here, Laura uses N1 by, and this happens by. Use N2 by, so just, you don't need to waffle in your biomechanics. Don't reintroduce the question terms. You don't need to write long statements. You don't need to build around your answer. Get your answer on the paper and structure it in the way that I've shown you here. And in terms of the planning, this would be more than enough to get you those 6 marks on that question, okay? Now, I think the only complex aspect of that is this part here. You know, we've said on this bit, it's not that in rebounding you're in a state of inertia. You could be. I mean, you could say that the duly accelerates upwards at constant velocity. You could certainly say that. But here I'm saying she's overcoming that inertia, that stillness, that constant velocity with a large force, with a large enough force, actually, I might want to say. Okay, so that's just, I'm effectively inverting or kind of turning on its head that law 1 and saying not that she's in a state of inertia, but this is how she got out of a state of inertia, which of course leads us neatly into law 2 also. Okay, that's enough on this part, straight back. So I clearly took far too long on that first part of this session. So let's do this bit pretty quickly. I'm going to focus specifically here on the graphical representation of these concepts of distance and velocity. Okay, so my focus here is to focus on that. We're obviously going to touch on notions of the units and the equations for these principles, but I'm ultimately going to focus on the graphs. So let's have a look here. So we're first of all going to look at distance time graphs. Okay, so distance time, that's what we've got first of all, distance time graphs. And look out for these in your exam questions, because I have found, again, they're simple concepts, but sometimes trip students up for some reason. So let's have a look at these in a bit of detail. So look, let's take example number 1 here. We have got the idea of a stationary object. Now that does not mean your pencil, pens and your rulers that you have in a lovely pencil case. It means an object that is not moving. All right, and we see here that effectively, if we've got distance on the y-axis and time on the x-axis, what we should see from a stationary object is that the distance traveled does not change as time passes. So look, time is passing like this. Okay, time is passing there. And the distance, you know, whether it goes up or goes down, the distance traveled is remaining what? Constant. So in other words here, we've got a stationary object. So what would be an example of this? Somebody waiting at a sprint start, a balance, a rugby scrum. All of these would be, assuming it's not moving, of course, all of these would be examples of how we'd see this distance time graph actually playing out. Okay, so the start, before the gun goes in 100 or 200 meters, we'd expect to see this kind of shape because there's no distance being changed or traveled as time passes. The only sort of aspect of that you might want to be careful of course, we don't tend to measure time before the race actually starts, but nevertheless. Here what we've got is a different principle for number 2. Here we've got the idea of constant velocity. So think this idea through. As time progresses, we should have distance going up proportionally. Okay, we should have distance increasing proportionally. Okay, so what do we find here? We find that here we have time passing and distance increasing proportionately to that time. So as a result of that, we could define this as something like middle of a sprint. We could describe this as some kind of top speed. And here's an interesting one for you. Think about this one. A shot put in flight. Now remember, we're not drawing the direction of the shot. We're drawing the fact that the shot is traveling a certain set distance within a period of time. Okay, so this would be really a good example of a shot put in flight. Now, if we let's imagine that this here is the landing point of the shot. What would happen to the distance at that point? What would the curve actually look like? And you might be able to say that at that point then, the curve effectively carries on like that, because of course the distance until the shot is actually lifted off the ground doesn't move. That's assuming it sort of stops dead, it doesn't roll on. But we'd expect the distance to stay at that point. This point, what's I think world record holders for women's about 19 meters 50. So let's say that this is 19 meters 51 here. Okay, the shot would travel through the air, would land at this point here, and then would remain at 19 meters 51. In other words, we'd get a constant velocity followed by stationary object. So you can get kind of compound graphs, and it's interesting to think about it in that way. This is what we would describe as number 3 here. This is what we describe as an accelerating body. So the distance covered is increasing per unit of time. Let me write that in for you. Distance traveled is increasing per unit of time, or per second, you could say, of course. So if we look at this second here, for example, between here and here, okay, the distance travelled only goes from here to about here. Okay, if we look at this part here, if we were to track this up, okay, we can see here that all of this distance is increased within that period of time. Okay, within that period of time, we've got this amount of distance compared to this little amount of distance here being actually travelled per that unit of time. In other words, the body is accelerating. We can see that by the shape of the curve. And fourthly, and finally, we have a decelerating body here. So again, what we've got here is the distance travel is, we just literally changed that word, decreasing per unit of time. And of course, what we've got at the top of this curve here, we've effectively got our stationary body here, haven't we? Okay, we're now on to stationary over here. Okay, here we've got the body is decelerating until it effectively stops moving there, and it ultimately slows down to a static point. And again, we've got the distance travelled is decreasing per unit of time. Now, here's some compound graphs. We might expect a graph like this for something like an amateur sprinter. You know, if I was to sprint 100 meters, certainly 200 meters, but even 100 meters, what would we find? We'd expect to find part A, which of course is a shape of acceleration. Remind yourself above, we have this shape is happening here, acceleration. We then have this red section in the middle. We know that this is the time and the distance travelled are proportionate. So this is what we call constant velocity, or we might want to call it terminal velocity, top speed. My top speed is not particularly high, unfortunately. And then here we have the distance travelled is decreasing per unit of time. So of course here we've got deceleration. In other words, we've got three distinct stages within our performance here. Let's call this 100 meters for our argument's sake. Okay, we've got three distinct stages, and we can illustrate what's happening with a distance time graph. Now, this is exactly the same, apart from this is what we might call an elite performer. And what is the difference here? Well, the difference is that they accelerate, perhaps they accelerate more rapidly, and of course they hit terminal velocity, constant velocity, and that continues until the end of the race. Remember, this point here is the end of the race. Okay, and if we track it down, you know, we're getting down to something like 10 seconds, that elite level, something between, well, I mean, world record levels is what is Bolt's men's record, something like 9.57 or something like that at the moment. And of course, then the women's world record comes in around about 10.5, I think it is. And then, of course, a lot of 100 meters for both men and women get run between 10 seconds and about 11.2 seconds. Okay, so this kind of elite level here, you're not going to get, at 100 meters at least, you're not going to get that kind of deceleration curve off at the end, because they don't slow down as they finish, generally speaking. Now remember, that is for 100 meters. Now if we come down, of course, we're going to look at here in a second in this question, you'll notice that we've got that shape, but this is an elite sprinter. Josh is elite sprinting, but he decelerates at the end. Okay, and that's because he's a 200 meter runner. Okay, or he's running at 200 meters there, but more of that in a second. So let's now have a look at velocity time graphs. And again, this might be the bit you find confusing, because you're thinking, right, I've got those distance time graphs. They seem really sensible. I get that. How then do I link? How can I differentiate these to with the velocity time graphs? Well, the key thing is being able to accurately interpret the graph. If it confuses you that this one and this one look the same, the reason that is happening is because we don't have a clear enough concept of distance and velocity, and that's the bit to ultimately work on. So let's have a look at this first one as an example. So number one, we've got here constant velocity. So we're saying that as time progresses, velocity is consistent. In other words, it's constant, so therefore it's constant velocity. Now in this case, we've got constant velocity here, it's at whatever x meters per second. Okay, so this could be something like middle of a race, as we've looked at before, middle of a race. We could look at something here again, something in flight, so heavy object in flight, heavy object in flight. Okay, so something like our shot example, or a long jumper traveling through the air would be a good example as well. So we've got this constant velocity there. Okay, it doesn't change, but that does change if we look at example 2. And now we're looking at an accelerating body. And again, this time the rate of change, or the rate of change of distance, increases over time. So our velocity increases over time. Why? Because the body is accelerating. Okay, so as time passes, the rate of change of velocity is getting greater and greater and greater, and that is an example of acceleration. So we could be looking at examples such as ball leaving racket, or you could say club or paddle. There we could talk about something like start of a sprint, or we could be looking at something like ball leaving hand. Okay, they would all be characterized by this shape, this acceleration shape. Here we've got the deceleration of a body, so the velocity is decreasing over time. Remember, if this was at constant velocity, it would carry on like that. If it was getting faster, it would go like that. Okay, so this is decelerating until it comes down to 0. Okay, so we could be talking about something like tackle. You know, so someone's running forward with a ball in rugby, for example, and they are effectively at this point here. They are tackled until this point here. Remember this period of time. They come to be completely stationary from that point. That would be a classic example. We could be thinking about something like a catch. You know, the ball enters the hand here, and as the catcher cushions the ball into their hands, it eventually comes to rest as they slow the ball down and catch the ball. So those would be good examples of a decelerating body. You could also talk about, you know, like a sprint after the final, after the finishing line, I suppose, something like that. And this is one that really confuses students a lot of the time. That was number 3 there. This is what we call a change of direction. And it's probably the most difficult application of these particular principles. And it leads us to talk about what we'd call negative and positive velocity. Okay, so it's important to get this principle in mind. So think about this as something like a tennis player moving to their right to strike the ball and then shifting to the left. Or it could be someone who's jumping up in the air, and as they come back down to, as they reach their peak, they come back down and then land on the ground and kind of lower themselves down a little bit to readjust themselves. So here what we've got is, in this first part here, this part A, we've got what we'd call positive velocity. And if you notice here, we've effectively got acceleration, we've got a touch of constant velocity at the top, and then we've got deceleration down this side. Okay, but of course what would then happen as we push off in the other direction, we're still accelerating, but we've now got negative acceleration because we're now going in the opposite direction. Something like, you know, instead of moving to the right, which was this bit, we're now moving to the left, which is this bit. And then we get kind of like this little bit of constant velocity, and then eventually we decelerate again to get back here. And this could be, for example, our ready position. Okay, so we've got our positive and our negative velocity. Now, the only difference between this blue area and this red area, well, the blue area is bigger, so we reach a higher peak velocity, for example, and the red sort of salmon area is exactly the same. We reach a lower peak velocity, but in this case we're going in a different direction, and we can illustrate that in this way. Let's have a look at the question. Now, first of all, I need to correct a mistake. There's this word here, I think yours is actually correct, but mine's wrong. This says velocity time graph. We're actually looking here at a distance time graph. So Josh, our sprinter, recently raced in a 200-meter event and produced the following distance time graph. Accurately describe Josh's performance at the start, middle and end of the race. Well, if we're going to describe things, we're going to say is characterized by. We're going to say is composed of. We're going to say is like. We might even just say is. We're saying what the thing is, what its characteristics are. The characteristics of the shape are, it is characterized by. Let's have a look at how we go about answering this. We already know this shape is basically this one, right? So we already know we've basically got this principle here. So let's see if we can actually put it into writing. So we've got here, we're going to break it into 3 parts, which are going to be the start, the middle, and the end. So let's have a look at how we get on. The start, so no introduction here, I'm just going straight into answering. The start is characterized by, so I'm describing, is characterized by acceleration. So first of all, I'm going to say that the start is acceleration because the rate of change of distance is increasing. So I'm saying the rate of change of distance is increasing, therefore we've got acceleration. And again, I'm probably going to end up with a submax there. I'm probably going to get 2 marks maximum for the start, 2 marks maximum for the middle, 2 marks maximum for the end of the race. But it's nice and simple there. I'm not going on about this. I'm saying it's acceleration. Why? Because the rate of change of distance is increasing. Okay, simple, done, move on. So now we're going to look for our next 2 marks. The middle is characterized by, so I'm describing again, constant velocity, or we could call it terminal velocity. I know this because the rate of change of distance is proportionate with the time passing. Exactly what we looked at above. Nice. Thirdly, the end is characterized by deceleration. Okay, great. How do we know that? How do we know that this part is deceleration? I know this because the rate of change of distance is decreasing as time passes. So I've shown my understanding of distance time graphs. I've been able to apply it to this specific curve. You know, if this curve had looked like this, for example, the end of the race, let's say this point here to this point here, would again have been constant velocity. But we don't have that, do we? We have a decelerating body and we have to express it in that way. Now, as I said before, this is a 200-meter race here, so we might expect the runner to slow down a little. Depends how they've tactically run their race, I suppose, but in this case they seem to have run like a sort of what you might call an average race structure, where they've gone out, they've accelerated hard at the start and they've tried to maintain their speed at the end but haven't quite been able to manage it. But there I'm describing the different features of that graphical format of distance and time. Okay, so we're looking at fluid dynamics here, and I guess the first thing we need to do is understand that by a fluid we can really mean 2 things in terms of a sporting application. One fluid is we're talking about the air. That's the one we're going to talk about pretty much for the entirety of this particular session, but just be aware we could also be talking about fluid dynamics within water, and the principles are basically the same but with a slightly different application. We're going to focus hard on fluid dynamics in air, but just be aware that you could potentially just need a broad understanding of fluid dynamics in water as well. The first thing we're going to do is we're going to look at factors affecting air resistance. So air resistance is a vector which acts, or a force which acts on moving objects which are traveling through the air. So something like a ball or a shot moving through the air, something like a human being moving when they're running or cycling or whatever through the air. These sorts of things experience a force called air resistance. And of course, one of the factors that we know causes a change in air resistance is speed, or really what I should refer to as velocity. So we probably already sort of know intuitively that the faster, for example, a racing car goes, the greater air resistance it experiences. Or if we take something like a shuttlecock, which leaves a badminton racket very, very quickly at very, very high speeds, it experiences quite a significant air resistance because it's traveling at that potentially kind of 200 miles per hour kind of rate. So the faster something goes, the air literally becomes like thicker, stickier at that speed, which if you want to sort of apply it to a real world setting, it's why when something's moving very, very fast, let's take a racing car as an example, to get a few more miles per hour faster, it needs a massive amount of additional power or reduction in weight to achieve that output, because at the upper end it's harder and harder and harder to achieve greater velocity within that sticky, almost becoming solid air structure. So speed and velocity is very important. The faster something's moving, the greater the air resistance. Secondly, we've got what we refer to as cross-sectional area. Cross-sectional area. So this would suggest that something with a very broad cross-sectional area is going to have a higher air resistance than something with a narrow cross-sectional area. We know this because, for example, a track cyclist is going to get into a tuck shape and to reduce their overall cross-sectional area that's hitting the oncoming air in order for them to reduce air resistance and go faster. Now, it leads to another point, which is that of shape. Objects with a broad shape, very much a similar sort of notion, experience more air resistance, assuming all of the factors are the same, such as the travelling at the same speed and so on and so on. Assuming that is the case, then the bigger the shape, the greater the air resistance. Again, come back to the notion of aerodynamic positions in different sports. I also want to talk to you about what we might loosely call surface characteristics. Surface characteristics. Surface characteristics. And what we mean by surface characteristics is if something is rough or smooth. And something, let's come back to our shuttlecock example as a really good one. A shuttlecock travels very, very fast. It has a broad cross-sectional area. If you think about like the whole, the base of the shuttle, where the feathers are at the widest part, it's got that kind of a cone shape, or that broadening cone shape. That, how would you call that? Not pyramidal. What's that cone type shape? And its surface is rough. Okay, so all of those things promote greater air resistance. And the last one, and I just be careful with this one because it's a relative concept, is the idea of weight. And what we generally find is that the heavier an object is, take something like a shot from shot putting, it will mean that the slower it travels, generally speaking. So we often find the heavier objects have less air resistance. Why? Because they're traveling relatively slowly. So they are the factors affecting air resistance. So of course we can manipulate those factors. We can make our cross-sectional area smaller when we are cycling. We can make our surface characteristics smoother when we are swimming, the water example, or when we're running in lycra, for example, a sort of sprinting notion. We can, all those sort of notions help to promote air resistance if that's what we wanted, or to limit air resistance, and we can do that in the ways described. I'm struggling a little bit here just to see my board properly. Now, this is where we, in my opinion at least, we get to some really, really interesting stuff. I want to talk to you about the principle called Bernoullis Principle. Just hang on one second for me, guys. You're going to hear me rustling about just for a second. So I just need to change something where I am. Just bear with me a minute. I would imagine you just heard some unusual sounds. I just needed to change the lighting in the room because I basically couldn't see my screen for a minute there. So that's much better. Let's crack on with this. So I was talking about the Venturi meter, and I'm particularly interested in developing with you an understanding of what we're going to refer to as Bernoullis Principle. Okay, and you, by the way, can experiment with this in numerous ways. If we get time, I'll explain them to you. But this was the way that the experiment was initially set up. And by the way, it teaches out there, in lessons I've done in many occasions in the past, we've literally built these Venturi meters and experimented. I've actually tried to make these things. You can make them in all kinds of funky ways if anybody wants to look into it a bit further. But basically, the experiment worked like this. Bernoulli, bless him, he set up a bunch of fans. Let me draw some ropey fan-looking thing. Look, he set up some bunch of fans and he fired air into his Venturi meter, which is this object here. And you'll notice that at position A, on 2 occasions, the actual the outside of the Venturi meter is nice and wide. You can see here, for example, this area here is nice and wide. Okay, and at point B here, as the air fires through, it actually narrows down into this point, and this is why this is important. So what Bernoulli did was the following: he fired air into this sort of channel, and he set up little sensors. Sensor here, and for example, I'm not being exact, okay, but sensor here. So imagine that this is sensor B, and this is sensor A over here. And basically what we can be confident of is that the air moving in this middle part is travelling faster. It's being squeezed down into a narrower channel, in this case almost like a tunnel. And of course at that point the air speeds up, and you can see why that would happen, because it's having to be pushed and forced through a narrow gap. And here the air is slower. And here the air is slower because it's in this wider area. It's not being pushed into a smaller place. But this is where it gets truly fascinating. Where the air is faster, the sensors, these barometers, showed that the air was at lower pressure. Okay, and where the air was slower, Bernoulli proved that the air was at higher pressure. And often when I've told students that, they've gone, no, that camera, that doesn't make sense. Air moving faster should be higher pressure. But actually, we can experiment in this way, and we find that faster moving air means lower pressure. Slower moving air means higher pressure. Now, if we start to apply that to a sporting example, if we can create a higher pressure above or below an object and a lower pressure on the other side, we can either create a force that's going to kind of lift it or pull it downwards, because we're going to get a pressure differential on each side of that object. Okay, why? Because if there's faster moving air on one side, we're going to have lower pressure. If there's slower moving air on one side, we're going to get higher pressure. So how do we apply that? By the way, before we move on to that, can I just suggest to you 3 ways? I'll be careful what you Google when you're looking into this, but you can have a look at paper blowing to prove this principle. It does work really well. You can have a look at balloon bouncing, which is a nice little experiment to prove this principle as well. And you can, have a look at those 2. There's a couple of others as well, but have a look at these. Have a look at these these little practical experiments, and you can actually prove this idea to yourself. I'm not going to get into it now because we don't really have time. So what I am going to get into is the flight path of a javelin. Okay, so here we have a javelin. A couple of things I want to express to you first of all. The javelin, this grey object in the middle, before we even get to these airflow lines, it has been presented with what we call, what am I doing? It's been presented with what we call an angle of attack. Okay? An angle of attack. And what we mean by that is that this javelin has been presented in a format that we would call an aerofoil. Okay, more of which in a few moments' time. But just accept from me, I'll explain this in a second, that this javelin has been presented with an aerofoil. We've also got on our image, and it's absolutely crucial you do this, a direction of movement arrow. Notice we had our DOM, you can just write a DOM in your exam if you prefer, direction of movement arrow. So we know that the javelin is going over there. So it's been thrown from somewhere over here and it's going to land somewhere over here. What's the world record? I think world record for women is about 82 metres. For men it's about 94 or 95 or something. So it's a big old distance that these things travel. So what are we looking at here, and why have we got this lift force illustrated? So this is what I'm interested in. This javelin is moving through the air. We have got an air molecule, which I'm going to make like a little red air molecule. And let's say that it's here. And let's say that it's here. Just look at these 2 for a particular moment. So as this javelin travels that way, it's going to displace these 2 air molecules. It's going to kind of hit them, and they're going to kind of blip round the back until they sort of spin off the back of the actual javelin. They're going to end up sort of over here somewhere. Okay, but we know in reality they're basically in the same place, but it's just the javelin's moved past them. But in order for it to do that, the javelin's got to kind of push them out of the way and get them around the sides of the javelin. And this is how it works. This one here, it's going to arc up and over the javelin, and it's going to end up over in this point here. Now look at the path that has followed. It's actually travelled quite a long way. This one here has travelled much less distance to get to this point. So underneath the javelin, we have less distance travelled. Less distance travelled. Above the javelin, we have greater distance. Greater distance travelled of the air molecule. Okay, so below the javelin, because we've got less distance travelled, that air molecule has had to travel slower than the air molecule at the top, which has had to travel faster. Bernoulli told us that if an air molecule is travelling slowly, it operates with high pressure. And Bernoulli told us, using his Venturi meters, he told us that if an air molecule is moving fast, which has had to go further, then we know that it has low pressure. So now what do we have? We have low pressure above, we have high pressure below the javelin, and as a result of that, we create what we call a pressure differential. A pressure differential. In other words, Whoops, I spelled that incorrectly. In fact, I specifically forgot my I. So we've created a pressure differential. Come on, James. A pressure differential, high pressure below, low pressure above. And because of that, we create this lift force up. And we can call that lift force a Bernoulli force, or a Bernoulli lift force. Okay, now what are the impacts of this? Well, impact 1, we increase, up arrow, horizontal distance. Okay, so the javelin, which is exactly, of course, what the athlete wants to happen, travels more horizontal distance. It goes further. We can also say that we get a deviation in flight. And because of that, we can call this an asymmetrical flight. So if you can imagine, something heavy like a big rock or a shot from shot put, if you can imagine that it literally travels in like a true arc in that way, well, what we've got here with our javelin is it's kind of gone like that and landed over here. We've got an asymmetrical flight, and we can call that, another nice word for it is non-parabolic. A parabola is an arc. And again, I'm managing to spell it incorrectly because I'm rushing. Forgive me. So we've got James, honestly, non-parabolic flight. Why? Because we have an elongated flight path. The flight path's been elongated. Why has it? Because we've got this lift force effectively encouraging the javelin to float for longer, to keep going for longer, to stay in the air for longer. And that's why the javelin throw will always present the angle of the javelin with an angle of attack and with what we call an aerofoil. An aerofoil simply means that the air travelling over the top of the object has to travel further than the air travelling underneath the javelin. And something like an aeroplane wing at takeoff works in exactly the same way. Okay, you might want to think about, I'm not going to get into details of that, but you might want to think about that. Now, a couple of points that I want to add to this. We could be talking about other examples. Okay, I mean, you might just want to sort of, especially if you're in a group now, sort of shout at each other what you think they might be. But examples that you could apply this further to are things like a discus thrower, a discus being thrown through the air. It's effectively, if I try and draw some shaded discus here, well, that didn't go well. If I try and draw some discus, it's going to be kind of thrown like this. It's moving in that direction. And again, we've got I'm not drawing it very well, to be honest, but you get the idea. We've got the same shape there. Another example you could think about is that of a ski jumper and the positions that they assume to make this exact shape. The only difference with the ski jumper is they've kind of got legs here, haven't they? So it's almost like, if this is the body here and this is the legs here, they kind of do it like that, don't they? They sort of lean everything forward, and the air works in exactly the same way. They make the same shape effectively, so you can apply it that way. The other thing I would say to you as well is just be aware of what we call an inverted aerofoil. An inverted aerofoil basically means that the angle of attack is upside down. Inverted means the other way around, or upside down. So if we were to look at something like the rear wing of a racing car as an example, you get the exact opposite. The air travelling underneath the wing has to travel further, and the air travelling over the wing travels less distance. So what does that mean? It means it pulls the car down through what we call a Bernoulli. By the way, we call this a Bernoulli lift force down. So just be aware of that. So I'm not going to get into. We've got whole tutorials on that on the everlearner.com. So have a look at that if you're interested. All right, let's move on. I want to look at this question here. It says, in the box below, draw an airflow diagram that represents a javelin in flight. Represent all forces acting on the javelin. So look, you guys have to develop the skill of drawing. I know some of you don't want to and don't like it, and I don't personally particularly like it either. But it's something you have to get used to. And don't be afraid that, your drawings aren't going to be good enough or they're scrappy. In that exam, everybody's sketching ultimately. So everybody's a bit sketchy. And to show that to you, I prepared mine in advance. But look, there's my javelin. It's rubbish. Okay, it's a really bad picture of a javelin. But it's there. Look, I've got my javelin. What have I got there? I could be using the words angle of attack, aerofoil. All I've put in there is like a scrawny little kind of like holder. What do you call it? Like the handle. What's the word I'm looking for? The grip of the javelin. I've got my direction of movement arrow. That's important. Let's look at what I'd include next. Look, I've put my first two airflow lines in. Notice that I've got my start arrows and my end arrows both pointing in the same direction, in the opposite direction of movement. That's important. But it's clear my air going over the top is travelling further, my air going underneath is travelling less distance, so faster over the top, slower underneath. Next part, I'm going to kind of complete this by putting my other lines in. Now, a couple of just little details in here. Do you notice in this little area here, my lines are close together? Why? Well, these are pressure lines, okay, or what I call isobars. And what that actually means is if they're closer together, it literally means lower pressure. Okay, so it's nice to be able to feature that in your answer if you're able to. Now, let's start putting our all of our forces, remember, all of our forces on. Here's my first one. This thing has weight, so the weight acts straight down towards the centre of the Earth, and I label it W. More about vector drawing in our last revision session on Thursday. My next vector I'm going to put in, I've got my air resistance arrow. This is not travelling hyper fast, this thing, but it's got a bit of speed, a bit of velocity, so I'm putting air resistance in there. Next one, of course, we know I've got my Bernoulli lift force, which is lifting the Javelin, as we talked about a moment ago. But notice down here, I have been given a bunch of space. Let me keep my image in play. I've been given a bunch of space. So what I want to do here, of course, I think I've moved my canvas, actually. Forgive me, folks. Not meant to work like that. So my lines down here, I want to use this to really summarize what I've drawn in case I've not made it clear enough in my drawing. So now, notice how much content one can get into two basic sentences. Let's read it together. Okay, the Javelin is released with, let's just mark what the correct language would be. With an angle of attack in an aerofoil position, air over the Javelin travels further, air over the Javelin travels faster, and according to Bernoullis Principle, let's name it, at lower pressure. So all of that is basically one sentence. Okay, that's how biomechanics can get us marks quickly. Air under the Javelin travels less distance, slower, and is at higher pressure, creating a differential and a lift force up, a Bernoulli lift force up, which causes James, this should say non-parabolic extended flight and greater horizontal distances travelled. So look, I'm not saying every one of those circles is going to get me 1 mark, but I'm only looking for 8, and I've made a mad amount of detail in just 2 sentences. That's how biomechanics can serve as well. Now, what I want to talk to you about is the image. This is going to be a mark for me. The fact that I've got the lift force is going to get me a mark. The fact I've got the air resistance and the weight force, they're going to get me a mark. The fact that I've got less distance under is going to get me a mark. The fact that I've got greater distance over is going to give me a mark. The fact that I've got my bars closer together is going to get me a mark, and so on. And anything I've got left, I've now explained it. I'm probably going to get a mark for the whole thing because I've got the angle of attack in there. How many is that? 1, 2, 3, 4, 5, 6, 7. And my last mark is going to come from one of those. One of those is going to pick me up that 8th. So can you see, for me, how that basic principle that we've got up here, a simple drawing, which I've simply gone through the process of producing for you, and 2 sentences literally kills that answer and gives a brilliant, kills that question, gives a brilliant answer to that question. I've clearly drawn what's required. I guess theoretically, I could do a vector resolution of all of these, but it hasn't asked for that, so I'm not going to do that. More of which again in the session when we come to the vector drawing, which is on Thursday. But I've clearly answered the question. I've clearly got enough content in there, and that would be a really, really high-flying answer to that particular question. So the good news about this magnets effect topic is that it feeds directly from those same principles that Bernoulli presented via that Venturi meter experiment that we discussed a few moments ago. So there shouldn't be anything, conceptually at least, which is new or different here. What we do need to gather an understanding of, however, is the impact of spin. And the impact of spin on the flight path of objects in sport. So a classic example is going to be something like a golf ball or a tennis ball or something like that. So let's first of all look at this little image here. we have got a golf ball which has been hit kind of off the centre of mass. If this is the centre of mass here, we can see that this contact point is off the centre of mass. So as a result, this ball is going to spin over itself. Now, top spin in golf is a relatively rare thing. Something like backspin is relatively common. Side spin, huck and slice, is also relatively common. But let's just, in fact, let me switch to the backspin example here, because it's probably a bit more realistic in the golf scenario. This image would really represent a mistake in golf. But here, for example, we've got an impact which is outside of the centre of mass. And of course, we can call that an eccentric force if we want to reflect back on our different types of motion, creating what we'd call angular motion. In other words, the ball begins to spin. And of course, we can see here the ball is spinning in this direction. We would call this anti or counterclockwise. So it's spinning in an anti-clockwise direction. It's spinning anti-clockwise. Now, the key thing I'd like you guys to grasp out there is that that ball alone is not spinning anti-clockwise. It's spinning with something else. And the key principle I'd like you to grasp, and I'm going to do it in some kind of pink colour, not that the air is pink, is that this ball is spinning with a boundary layer of air. So in other words, that sort of pink dotty bit is what we call a boundary layer. And that boundary layer is a layer of air which is effectively caught or stuck to the ball. And as the ball spins, the boundary layer also spins with the ball. And for that reason, we can begin to apply these principles to the principles of Bernoulli that we looked at a few moments ago. Did something just flash up on my screen there? I'm not totally sure what that was. Never mind. So let's move on. So last things before we kind of look at this technically, this example here would be top spin, more of which in a second. This example here would be back spin, again, more of which in a second. This example here, we're actually looking at the longitudinal axis from the top. This is the top of the ball here this time. So this is, if we're talking about a right-hander, a golfer who's playing right-handed hitting this ball, this would be what we would call huck, or sometimes we call it draw in golf. And this one where the ball's kind of like going off in that direction there, this is what we call a slice or a fade. Okay, and they're deviations within the flight path of the ball. All of those represent a deviation. So let's have a look at how the principle actually works. Well, let's have a look at our golf ball here. This time we've got our top spin. So here's our top spin. We've got a golf ball, but indeed it could be something like a tennis ball or a table tennis ball equally. Remind yourself that we've got the boundary layer spinning with the ball. Okay, so there's the boundary layer spinning with the ball. It's spinning now in the clockwise direction because we've got here top spin. Okay, we've got direction movement to the right. The ball is spinning with top spin. Now, of course, what's going to happen here is that if we take 2 points on this ball, let's take this point here and this point here. Okay, at this point here, the boundary layer is actually spinning in this direction. Okay, in other words, it's spinning with the air, and that's going to promote fast moving air at the bottom. Start to think about what fast moving air means according to Bernoulli. Meanwhile, the boundary layer up at the top of the ball here is spinning in this direction. In other words, it's hitting the oncoming air, it's colliding with the oncoming air. And as a result, the air up here is slowing down. It's traveling more slowly. So we have fast moving air below the ball, slow moving air above the ball because the boundary layer is colliding with the oncoming air. Remember, it's the boundary layer colliding with the oncoming air. And as a result of that, we effectively achieve once again that concept of a pressure differential, not this time because we've got an angle of attack as we had before with the Javelin example, but now because the boundary layer is colliding above the ball. So what does that mean? It means that we produce a lift force down. In this case, we call it a Magnus force. So that is how topspin works. Now, if this ball was traveling if this was like the arc of the ball, that's how it was going to travel like that. What's going to happen here, I'll just change colour to sort of orange. What's going to happen here is the ball is going to travel like this. And rather than landing here, it's going to land here. In other words, it's going to shorten the flight path. Okay, so a couple of things about topspin. First of all, it's going to be pulled down to the ground by the Magnus force. It's going to shorten the flight path. We can call that, as we know already, asymmetrical. Asymmetrical. It's non-parabolic, non-arc-like flight. Now, when would we use this in a sport? Let's think about something like tennis for a second, or table. What am I doing? I'm just speaking. I'm trying to go too fast here, guys. So, tennis. Let's think about something like tennis. When would we use topspin? Well, we'd use it as an attacking shot. Okay. Now, it works really, really well as an attacking shot because it's a fast travel. Or in other words, it's fast through the air. We can also say it goes high over the net. One of the things about topspin shots as well is that if we've got a kind of a tennis court here, and here's the net, we're kind of looking at it sideways on. The topspin shot will actually, let's say it's leaving here, the topspin shot will go high over the net and dip down. Okay, it kind of works that way and land nice and short. Often you're looking for it to land somewhere over here, but the point is it's going high over that net. That is an advantage because it's less likely to hit the net. We've got this idea of a shortened flight path, shortened flight. So we can also say it's less likely to go long. And as a result of all of this, it forces opponent back. Okay, so that's why we would use something like a topspin shot in something like tennis or table tennis. Now in golf, even though that's our example in the picture, a topspin shot is nearer to making a mistake. It doesn't do a lot for us. There might be very, very odd occasions where we might aim for a topspin shot if there's a really unusual shot being played, but generally speaking, that's not the case. If we look at exactly the same situation now with the backspin, we're going in the same direction, notice. Now, of course, our boundary layer is here, exactly the same. That's actually even air held in the dimples of the ball, of course. So what we've got here is that at the bottom of the ball, here we've got a collision of air. So down here, we're going to have slow moving air. Okay, slow moving air. Up here, we've got the ball, the boundary layer traveling smoothly with the passing air. So that's going to make us fast air. So here, of course, we're going to have high pressure. Here, of course, we're going to have low pressure. And again, we've got our pressure differential. So what do we get? We get our Magnus lift force this time. So now, I'm not going to write in all of these points again, but now with our backspin shot, we get a completely different situation. Now, with our lift force, we've got, well, let's actually put some points in. Why not? Why am I saying I'm not going to do it? So now, we have our Magnus force from our, in this case, it's a lift force, and we have that because of that pressure differential. We have an asymmetrical flight path. My spelling today is ridiculous. What am I trying to do? The spelling of asymmetry has gone out of my mind completely. Asymmetrical flight path. And again, we can call it non-parabolic, but this time we can say that this time the flight path is lengthened. Okay, if this was our sort of parabolic flight, if it was going to travel like this, okay, what we'd find now with this example, with the backspin, it would fly flatter and longer. Okay, flatter and longer. And that's one of the impacts of backspin. Okay, it's one of the impacts of backspin. We've got this lengthened flight path. So a couple of things about backspin. It travels slowly through the air. Why is that advantageous to something like a tennis player? Well, we can recover position if we're out of position. So if we're out of position and the ball travels slowly through the air, of course it allows the tennis, so this is going to be like for a tennis example here. So it allows the player to recover position. We also say in terms of the backspin, it travels low over the net, which can be, it can be risky as well because it may hit the net, but it's also advantageous in the sense that it keeps the player low. So it goes low over the net. It has an extended flight, which we can say means it will land deep in court, deep bounce. So of course we can use that backspin for those particular reasons. So the key thing I would say to you guys is this topspin and this backspin example, and I'm going to look at how it influences bounce in a second, but it gives us clear advantages in certain circumstances, especially in games. Now the backspin in golf is beneficial for a different reason. I'll show you that now. Let me actually open my toolbar and let me grab. So let's assume that this is the ground. Okay. So what we're going to do here is we're going to take a ball. Let's make it some kind of green ball. I guess we could argue it's a tennis ball. Okay, we're going to take this green ball, and what we're going to say here is that the ball is going to travel in and it's going to hit the ground like this. Okay, so it's going to travel in and it's going to hit the ground like this. Now the thing I'd like you guys to realize is that if the ball has no bounce, it's going to bounce. If the ball has no spin, it's going to bounce out at some kind of angle like that. Basically, the same angle at which the ball comes in, depending on the surface. Okay, so this one here is what we'd call no spin. All right. Now, if we hit the ball with backspin, which of course means that the ball is rotating in that direction, if the ball is traveling to the right across the screen, well, this time what we're going to get is the ball is going to come in. Let's assume it comes in at roughly the same angle. Okay, and it's going to come in there, and this time it's going to do a different position. It's going to end up in this kind of position here, and the reason that is because it bites on the ground. It creates additional friction on the ground and actually sits up and bounce and kind of shortens it on its bounce. Whereas if we were to do the same thing with a top spin, it would, let's say it comes into the same place, it would come and push the player back in that, so it sort of kicks on in that situation. So we would have that our backspin would bounce and sort of shorten, which is why it's often used for things like drop shots in tennis and table tennis, for example. And the top spin is going to kick and push the opponent further back out of the court in that way. This one here is topspin. So that is the effect of spin on bounce, and it's useful for us to know that because again it can be a tool that a performer will use. Now in golf, the reason that the backspin one is relevant is because of course if the ball is traveling into the green, and I don't know, we've got let's say the flag is somewhere over here, you know, the flag is somewhere over here, the ball's going to bounce in here. And rather than sort of kicking on and kicking on and kicking on past the hole, it's going to hit, it's going to bite, it's going to bounce like this, and it's going to come to rest without rolling way past the hole, which is why that backspin becomes popular in approaching the green in golf, okay, because it allows the ball to prevent from kicking on past and overshooting the pin or the hole in this context, which a ball with without spin, or indeed a ball with top spin, would have more tendency to do that. Okay, let's move things on. I'm going to have a look at this big question here, and actually it's a funny one because in essence I'm actually just going to help you plan it out. Okay, so here we've got a very interesting question. Discuss the use of spin in tennis. Well, we've kind of touched on it. Use airflow diagrams to support your answer. So my first question to you is, what does the command of discuss actually want you to do? Now, when we get a discuss question, discuss simply means talk about key details. Okay, talk about key details. But usually hidden behind a discuss question is an evaluation, an analysis, a comparison, or an explanation, or some combination. So my question to you is, what kind of skill is this actually asking us to do? And for me, the tip-off is it's just said the use of spin. Now we know there's loads of different types of spin. There's topspin, backspin, side spin, our hook and our slice, for example. So we actually are looking here specifically at the skill of analysing. In this case, we've got to discuss, but we're going to analyse, but we're going to offer some evaluation, any negative. So how are we going to analyse? So to analyse things is to break it down into parts and explain it. So what parts am I going to break down into here? Well, I'm going to do these ones. Here's my sections, my parts, my analysis. I'm going to do a bit on topspin. I'm going to do a bit on backspin. I'm going to do a bit on side spin, hook and slice. And then I'm going to talk about the effective spin on bounce. So these are going to be kind of like my sections here. Let me change colour. These are going to be my 4 different sections of my answer. I'm going to break it down and do that. Now, the next thing I'd like you to have an awareness of is if I take the first one, for example, let's take topspin. I'm going to explain how it applies, and I'm going to ask, are there any negatives to it? Okay, are there any negatives? Now, if you think about what we talked about before with that topspin example, it's all of this stuff, right? So we're going to talk really about all of these points here, but let me give you a specific range of content that we would use to explain how topspin would apply in tennis. Okay, so here are at least some of the things that I would talk about. So these would be some of the points I would get into my answer. Let me just drag down slightly. So I would say that topspin, and you can just plan this out and you can think about how you'd write this into your answer. I'd say firstly, topspin is an attacking shot. It's useful because it goes high over the net and travels fast through the air, pushing the opponent back. The ball also dips in flight during a short and non-parabolic asymmetrical flight path. This is the case because we get a lift force or a Magnus force down. There's our Magnus force. Therefore, the ball is less likely to go long. It's more likely to land in court. And it forces the opponent deep in the court so that the player can follow that shot up with a drop shot. Can you see how all of that is simply going, right, I understand Magnus. There's all the stuff I know about Magnus and topspin. That's how I'm going to explain it. But there is a negative. So I want to put a bit of evaluation in. And the negative is this one. The harder you hit the ball using topspin, you can hit it really powerfully, but of course the ball's going to arrive at your opponent with lots of velocity. So of course when they hit it back at you, it's going to come back at you fast as well. So that's a negative there. So that would be like my first section of my answer. Well, what would be my next section? Let's have a little look here. I've got my backspin here. I've actually written this in, so you can see how that would be kind of planned out, listed out. Let's just go through my answer here. Secondly, this is like my second paragraph. Secondly, backspin is a defensive shot because the ball travels slowly through the air, allowing the player to recover position. All these are correct answers. The ball travels low over the net and has an elongated horizontal flight path, which is, can't believe I've done that twice in here, which is non-parabolic. Okay, which is non-parabolic. The ball experiences a Magnus lift force because faster moving air above the ball and slower moving air below the ball, see diagram, more of which in a second. The player uses the shot when out of position, so they use it to recover position, or against a baseline player to bring them forward. Interesting point, we might use backspin to actually bring a player who likes to play deep forward. Why? Because it does that kind of short bounce thing, remember. So it brings people who like to be deep forward into the court. Backspin is also used for drop shots. One negative, so here's my evaluation, is the tendency for the ball to go long. So because you've got an elongated flight path, the ball can tend to go long. Now look how concise that is. Look at how many correct responses I've got into my answer in what? 8 lines, 9 lines? I've got some like 12, 15 correct points. That is the beauty of biomechanics. You can get a lot of content in. Now, with regard to the drawing, this bit, if you're asked to draw, you must draw. And of course, what you guys are going to do is effectively, that was my backspin bit, you're going to draw this. Okay, so this is my topspin. You're going to draw this. This is what your drawing is going to be. Now, a couple of things. Remember to put your direction of movement. Remember to put your little arrowheads on all of the lines at the front and at the back. Remember to draw your Magnus force. Remember that wherever you've got low pressure, the lines get close together and they're further apart where you've got low pressure. So you're creating that pressure differential and you can see it in your illustration. So that, of course, that diagram effectively is going to go straight into there. So you can imagine my section. I'm going to describe, I'm going to explain topspin, I'm going to do a diagram, I'm going to explain backspin, I'm going to give a diagram. At the end of each of those sections, I'm going to give a negative, at least 1 or 2. Then I'm going to talk about side spin, and I'm going to do a diagram or 2. And then I'm going to do the effect on bounce, and I'm going to do a diagram. So I'm just going to go through that systematically and then ensure that I'm covering all my key points. Just one thing to finish off with, I kind of breezed over it earlier. Just right back at the start here, with these examples here where we've got our side spins. The only point I make is that if this is, let me do it like this. If this is how we've got the ball being struck from down here, okay? If this is with no spin, the way it works for our hook is that the ball will actually start out over there and it will travel in that direction for exactly the same reason that we've talked about already. We've got the pressure differential, but this time from side to side around the longitudinal or vertical axis. Of course, what we've got over here on our slice example, this is for the right-hander, it will work in the exact opposite way. It starts out on the left for the right-hander and then slices off to the right. Now, you might sort of want to see that that's a mistake, but think about how that can be useful for a footballer or a rugby player who's kicking at goal, for example, a footballer who's taking a free kick and trying to get it past a wall of defenders. Think about how it would be beneficial for a golfer, because of course golf, if this is the tee in golf, the green isn't always straight down here. The green may well be kind of hidden. The green may well be kind of like hidden over here somewhere. Okay, so they kind of have to sort of curve it round something, okay? And that's where like slice or hook can become really, really useful, an actual weapon or a technique that players rely on. And it's those kinds of understandings that you would need to both be able to describe in our answer, but also, of course, be able to illustrate within these spaces as well. So look, I hope at least that's a pretty comprehensive view of the Magnus effect. I hope that's been useful for you. I really enjoyed teaching this particular one. I hope you can forgive me the fact that I haven't gone through every single section of this answer. I mean, if you can sort of wrap that up, that thing there, and use that as a model for how you should write in biomechanics, it will serve you very, very, very well. Okay, because we're getting a lot of concise information into our answers. We're not waffling. Everything we're writing is content and relevant to the question that's been asked.
So vertical forces, folks, we've talked about them in numerous other circumstances so far, actually. I mean, if you think about it, especially if you did our show recently on fluid dynamics, we've already talked about these sort of principles as a basic construct, but I really want to get to like the depth of this and make sure we are hyper accurate with how we represent these. So, I mean, the key thing, I suppose, here is that we're going to talk about vertical why didn't I pronounce my T there? Vertical forces in two main structures here. There are others, by the way, but we are going to talk particularly about the weight force, and we're going to illustrate that, and we're going to talk particularly about reaction force. Okay, and specifically we're going to tend to talk about GRF, which is ground reaction force. And then what we really want to be able to do, we want to be able to illustrate those on a range of on a range of different free body diagrams. But importantly, we want to look at the relationship between these and what that tells us about the movement which is being displayed in the image. So I always think we have got three basic rules to follow, okay? And that is whenever we represent our forces, whether vertical or horizontal, or indeed we may have vector resolution within our drawing as well. But whenever we draw, we want to make sure and tick these off every time, especially early on when you go through this process, that your point of application of your vector or your arrow is correct, that the magnitude of your vector or your arrow is correct. Now, magnitude of a vector is represented by the length of that vector, more of which in a second. And finally, we want the direction of the vector to be correct. Okay, now you're going to hear me intrinsically talk about these 3 points as we start this process. So I'd encourage you, every time I sort of seem to do something or say something, bring it back to these 3 points, because this is ultimately the skill that you're looking to represent, other than the representative nature of the overall image. Finally, always include a direction of movement arrow. Every time we are illustrating vertical forces, we are looking to represent a direction of movement arrow. So let's go and have a look at our example number 1. We have some speed skaters here. I have to say speed skating is one of the sports I've never done in my life, so I may well show myself up here somewhat, but I think I have the basic understanding of it. And I also need here my toolbar. And my toolbar's up here, and we particularly want straight lines. We want to be able to draw straight lines. So let's go for this first of all. I first of all want to represent the weight force. I want to work on this performer here. We could the one at the back's basically the same, but I want to work on this performer here. I'm going to decide that weight force always originates from the center of mass. Okay, so I'm going to estimate that this performer's center of mass is approximately there. If in doubt, for a performer, the navel, the sort of belly button area, is an excellent point for the center of mass of a human being. Of course, you probably know, as the head leans forwards here and the arm is pushed out forwards and the front leg, you probably know it's kind of going that way a little bit, that center of mass, if you've studied the concept in more detail. But this is our representative point. Okay, if you were slightly to the right here, it wouldn't be a problem. Okay, so how do we now represent this weight force? Well, we want our straight line, and our weight force always acts downwards towards the center of the earth. Okay, so there is my weight force vector. I must make it an arrowhead, and I must label it. There's my weight force. Let me choose a different color. Let me choose red here. There's our weight force there. Okay, so I've got my arrow down. Now, what have I done there? I've got my point of application correct from the center of mass. The magnitude of my vector is down approximately to the level of the floor, in this case the ice. That is correct. Just a little technique here. If you're doing the weight of a human being, sort of a broadly accepted kind of biomechanical principle is it goes down to approximately the floor, very rarely beyond the floor unless they're carrying an extra weight. And finally, the direction of the vector towards the center of the earth, towards the center of the earth. Now, we also want to look then, and by the way, I haven't put my direction of movement arrow, and you might say, well, James, there is no direction of movement because this performer is not moving. They're stationary, they're in the ready position. Well, that's true, which is exactly why up here we write no movement. I'll show you an alternative to that in a second. So no movement is an example of a direction of movement arrow because there is no arrow to draw. Okay, so no movement. Now what we want to represent now is the reaction force. We know that from Newton's second law, every action every force, we could say, every action has an equal and opposite reaction. So if weight force is applying downwards with this length, this magnitude, we must have a reaction force which is equal in length and opposite in direction, okay? Now, what we're interested in here, of course, is the point of contact, which is the point of application, the point of contact between the performer and the floor, in this case the ice. So we've got 2 points of contact. We have one here, and we have one approximately here. Now, we now want to draw our reaction force vectors. Now, your first instinct might be, well, make it the same height as the weight force. So you might do something like that, and you might do something like that. Okay, and you might end up kind of illustrating these in that way and writing something like ground reaction force. Now the problem with that is that we don't have equally opposing forces. Would you agree? Would you agree that the ground reaction force as a sum of the ground reaction force is greater than the weight force? So what we want to do in reality, let me just skip back a bit. So what we want to do in reality is we want to do it like this. Now you, in your exam, are going to measure these exactly. I'm just going to estimate mine. We're going to have one there, and we're going to have one there, okay? And the reason we're doing that is that now my 2 ground reaction force vectors combined equal the weight vector. Would you agree with me? So the 2 ground reaction force vectors equal the weight vector. So in other words, if we take that plus that plus where am I? That big green arrow down, we get an answer of 0. More of which in a second. We get an answer of 0 because these all oppose each other. Now, if you want to get really, really technical, you could say to me, well, James, I think there's more weight on the front foot, so I'm going to make that one slightly longer and the back foot slightly shorter. Fine. I have no problem with that as long as you have the logic in your mind and the total of the vectors equals this concept. No movement. Now, in this example then, we've got 2 upwards vectors, the ground reaction force, and 1 larger weight force vector, and that produces a situation of 0 net force. Well, why is that the case? And the reason that is because we can say ground reaction force equals weight. Would you agree? Ground reaction force equals weight. And because of that, we call that zero net force. Now, zero net force is synonymous with the concept of inertia. So with inertia, we have two possibilities. Either the performer could be completely still, and that's what we've got here, or they could be in a state of constant velocity, more of which in a second. Okay, so it's one of those two things has to be the case if ground reaction force and weight force are equal. And of course, we're talking about constant velocity. How? In the vertical direction. Okay, in the vertical direction. This performer is neither accelerating downwards nor upwards. Why? Because there's zero net force acting. So start to think about applying that principle to something like a tennis ready position, a person standing still. And now let's think about it when we don't have zero net force. In other words, we have a net force. Let's look at that example. So something I'd like you to do here, we have an illustration here of a performer skipping, and this is I'm going to tell you a little lie here, but we are going to make an assumption that her toes are still touching this wooden panelled floor, okay? I know in the image they've just left, but we're going to assume, we're going to imagine, we're going to believe that the toes are still touching the floor. It's actually really difficult to get really high quality images just as the toes leave the ground. So we've kind of, we're making that up a little bit at times, but just accept that for me. That's what we're trying to illustrate here. We tried all sorts of ways of bringing this floor up. Some of you may be better at Photoshop than us, and we'll be able to do that perhaps. Anyway, never mind. Let's get on with it. So what have we got here? Well, first of all, I'm going to decide that this person has a direction of movement in this direction. Their DOM is upwards. In other words, they've got upwards motion. So now it's my responsibility to illustrate that in relation to this drawing, this vector drawing. Now I can already go ahead. What were my colours? I had pink. I can already go ahead and say that GRF is going to be greater than weight, because of course in this circumstance here, for movement to be up, the ground reaction force, didn't mean to make that green, the ground reaction force must be greater than the weight force. Okay, it must be greater. Just make sure you understand what greater than and less than and equal, what those symbols mean. So let's get on with it. So let's put our weight force in first of all. Let me get my straight line. Let's go for literally the belly button this time. Now let's go for a weight force vector. Again, just about down to the ground, just shy of the ground. There's our vector, and we're going to call that weight. And my green is not of sufficient strength. Let me just make that a darker colour. In fact, I'm going to go over this with something different. Let's try something different. Let's use orange. Going to end up looking a bit ugly. This, I'm afraid. May not be any better, to be perfectly honest. And there's my. What am I doing? That's a W, apparently. You're going to do. You can see how being neat in your exam is important, right? Because if an examiner looked at my pathetic attempts there, they might just think, what? So obviously you guys need to be nice and clinical when you do this. So again, my performer is taken off with both feet. So I'm interested in this because we're gonna say that. Let me try a blue. So we're gonna make this and this the contact point with the ground, okay, the points of the toes and the ground itself. And of course now what we're trying to represent is a greater ground reaction force than we have a weight force. Now they're both supposed to be completely vertical. Again, you will make sure that is the case in your exam, but would you agree with me that the combination of this plus this is greater than this? Okay, so in other words, we've got the ground reaction force is greater than the weight force, and as a result of that, we get this direction of movement up. And of course, we can even look at Newton's second law. Again, think back to our session on Newton's laws, and we can say the greater the ground reaction force, in other words, the greater the force, the greater the acceleration. So, in other words, the greater the ground reaction force, the longer these blue arrows are. Newton's second law tells us that acceleration will be proportionate to the force acting in the direction of that force. So on that basis, that F equals ma, on that basis, the greater the ground reaction force, the greater the upwards acceleration, and the greater the vertical distance travelled. Okay, which, by the way, you could simply say push harder jump harder, jump with more force, and you'll get higher. I don't think that's going to surprise anybody, is it? Okay, so that's the principle we're looking to be able to illustrate. But can you agree with me that by illustrating this way, we have shown that the direction of movement of this performer is upwards? Now, I often get a question at this point, which is, well, James, don't all forces have to be equal? And the answer to that is yes. We're making an assumption here of a third force, and it's what we'd call an action force. Now, we're not going to illustrate this on here. We've actually got an action force which is acting downwards here. Now, if you were to take those red action forces and the blue ground reaction force, you'd actually find it would equal the weight force. But of course, this performer can push harder to get a greater ground reaction force. Remember, the ground reaction force is going to be a combination of both the reaction of the weight force and the action force. Okay, so have a think about that. But just so you have it clear, generally speaking, we won't illustrate these action forces. We'll just show the greater ground reaction force and the great in comparison to the weight force. And again, sometimes students have asked me at this point, well, James, if all forces equal each other out, why does she accelerate upwards? And of course, what we're saying here, you've got to remember that this isn't just a wooden floor, this is the earth. Okay, now obviously, this is the earth here. The earth is a heavy, high inertia planetary object. So if it collides, in this case, with the feet of a jumper, the earth, which has huge inertia, is going to stay exactly where it is, and the performer, who's relatively light in this context, is going to accelerate away. Okay, if the earth and the performer were the same weight, the same mass, they both accelerate away. But of course, the earth is enormously heavy, and the performer is relatively light. So on that basis, she is the object that will move as a result of these changeable forces. Hope that's not too confusing. Let's have a look at a couple of examples. Right, what does your common sense tell you are the answers to these questions? Let's call this number 1, this number 2, this number 3. This number 4, and this number 5. What do you come up with answers to these? So a red downwards arrow like that, I guess it would be like a weight arrow, and a green ground reaction force arrow like that. What do they equal? What would you write here? And this is what I want you to write. 0 net force. They cancel each other out. This is going to be a state of inertia, or this is going to be in the form of stillness or constant velocity. What are we going to have in this example? Well, a slightly bigger up arrow and a slightly smaller down arrow. We're going to end up with a small up arrow. Okay, that's going to be the product, or the sum of this equation. Let's have a look at this one. Smaller up green arrow, a bigger down red arrow. But of course, we're going to get a small down red arrow as an answer to that. In other words, the performer is going to be moving downwards. They're going to be sinking. I don't mean into the ground, but almost as it could be, for example, that the performer is just preparing to go into a jump. You know that thing where you sort of go down first and then you come up. What about this one? A long up green arrow plus something equals 0 net force. Well, the only answer to that can be a down arrow of equal and opposite direction to the red arrow. So that's going to work for us. And what about this one? 2 long red arrows plus 1 longish green arrow is going to give us the same answer as the previous example. We're going to get 1 longish down arrow. So effectively, this one and this one cancel each other out, right? Leaving us 1. Okay, so that's the logic we'd like you guys to kind of grasp and to be able to apply as fluently as possible, please. Let's look at a question. So, illustrate all the vertical forces acting on a high jumper at the point of takeoff. And again, we took a long time to try and find this photograph. This is Blanca Vlasic, really high quality long jumper. I think she may have retired now, but very close to. But magnificent high jumper. Now, how would we illustrate this? Notice we are only interested in the vertical forces. So we are not looking at the diagonal action force. We are not looking at the friction horizontal forces. We are looking at the vertical forces. So what do I want to do? Well, let's get our basics in place. Let's do it really neatly here. What's my direction of movement? Well, even though I can't live with that. What's my direction of movement? My direction of movement is up. Okay, so I've got direction of movement. You're going to be marked on your memory of including that in your illustration. So direction of movement up. By the way, in reality, you probably have to draw the jumper as well. Just be prepared for that. All right, you might want to practice that specifically. Now what I want to do is I want to put my weight force in. So my weight force is going to be from approximately the centre of mass, and it's going to act downwards. Okay, so we've got our weight force approximately the same length as we've been doing all the way through. Okay, so there's our weight force. And of course, in this instance, high jump by definition is a one-footed takeoff, right? You have to take off one-footed in high jump, otherwise it's foul jump. So in this case, we need all of the reaction forces coming from 1 foot. So what we want to do is we want to illustrate the contact point, and let me change colour, it's not going to work. We need to illustrate the contact point between the foot and the floor. And of course, we're looking for a ground reaction force, which is greater. Okay, so we need a greater ground reaction force arrow. Okay, now what have we illustrated with the combination of our vertical forces? We've illustrated upwards movement. Okay, and the extent or the acceleration of that is going to be proportionate to the size of the force acting, Newton's second law. Okay, so there we go. We've got our marks. Now, how are they actually going to mark that? Well, you're probably going to get a mark for your direction of movement arrow. Okay, you're going to get a mark for the correct use of the ground reaction force arrow. You're going to get a mark for the correct application of the weight arrow, and then of course you're going to get a mark for the relative difference between the ground reaction force and the weight force, and that's going to give us our max. Now let's have a look at this. Making reference to Newton's second law. Oh my goodness, who's net 1? Mike, are you listening to this? So you put it in, and we didn't pick it up in the checks. Maybe we rushed that one. That's really embarrassing. Newton's second law. Okay. I can't live with that. Hang on. Newton's. It's owned by Newton's. Newton's second law. Describe. So we're saying what the characteristics are. Describe the motion that you have illustrated in the previous question. Now I've prepared this answer in advance. Okay. So I want to describe what I've drawn here. Okay, or at least the motion. The motion is characterized by. So again, I'm already describing upwards acceleration proportional to the ground reaction force and in the direction of that force. In other words, I'm taking Newton's second law, the acceleration of a body is proportional to the size of the force acting and in the direction of that force, and I get my marks by simply placing my example within it, and I get my max. Okay, now there is a bit more we could do here. We could say the greater the ground reaction force, the greater the acceleration. Okay, that would probably get us credit. Okay, and vertical distance travelled. The other thing you might want to add into here is you could simply say ground reaction force is greater than weight force. That's another point that you could add into this kind of answer. Okay, nice. So look, there's some key skills for you. They're actually nice and simple, but you have to be able to apply them consistently and, as we'll see in a moment, in more complex structures. Okay, good. So we're ready for this horizontal forces section. So couple of things. I want to firstly just address the same principle. Actually, before I do that, let me do what I did earlier on and say that for horizontal forces, they're actually... I'm not going to address water today, so I'm not going to address movement through water. The principles are very, very similar, but I'm going to address movement through the air only. So we're really interested in two horizontal forces today, and that is the notion of friction, and that is the notion of air resistance. Okay, now just be aware that if we were applying these principles to something like a swimmer in water, we'd also be looking at thrust and drag. Just as with our weight and ground reaction force, we'd have weight and buoyancy. Just be aware of those principles, but I'm not going to get into the details of that today. Now, I want to remind you that the principle that we looked at earlier in terms of resolving vectors is basically exactly the same. So what would we get for this first example? One small red arrow plus another small red arrow is going to lead to a bigger red arrow in that to the right direction. Okay, what about this one here? Smaller red arrow, smaller green arrow. Well, what do we have here? We have zero net force. Look at this next example. Two smaller green arrows, one smaller red arrow. It's going to lead us with one smaller green arrow. If you're not sure about this, you need to clarify this point. This one here, one smaller red arrow equals, with a gap, one smaller green arrow. So that can only mean that this is what's in the gap. Okay, scrawny drawn by me, obviously. And this last one, small red arrow plus something equals zero net force. Well, we already know what that one must be because we've basically got it up here at the top. and of course it has to be a smaller red arrow. Can I re-emphasize to you something I said before? If you were doing that for real, in fact, when you do that in your note, in fact, when you do that now, get your ruler out and measure it. I'm not joking. Get your ruler out, and I want it to the millimeter or better perfect, please. That is the standard you should set yourself. Now, okay, I know I'm not representing that because I'm scrawny doing it here. I actually do have a ruler up here, but I'm not very good at using it. And I just want to sort of move on and get across. But when you do this, you are going to measure it. Okay, please do that. So you need a ruler with you in the exam, of course, as well. Now, let's move on here. What do we have? We have a runner here who appears to be something like the middle of a long distance race, okay? Could be the end, but I'm going to assume that this is the middle of a race. The first thing I want to do is I want to illustrate that is my direction of movement, okay? That is my direction of movement, and just for the sake of argument, I just want to confirm I'm going to draw here constant velocity, okay? Constant velocity. So, let's think about this. Let's do our basics first. We have a weight force. We know it acts downwards towards the centre of the Earth. There's our weight force. We have, again, we're going to assume the foot is right now in contact with the ground. We have, let me choose a colour you're going to be able to see. We have a ground reaction force for our vertical forces, which is equal and opposite in direction. That is meant to be exactly equal to the weight force. Why? Because this performer is neither accelerating upwards or downwards. Yes, I know some of you are going to say to me, well, she does kind of go up and down in a wave if you look at the head movement. That's actually quite true. But for the purposes of this illustration, she's going to be not accelerating upwards or downwards in this illustration. We now have zero net vertical force. Would you agree with me from the principles we looked at before? Now this is where it gets interesting. She's moving reasonably quickly, not very, very fast, because it's, she's some kind of long distance runner. It's not a hyper fast movement, and human beings ultimately don't move fast in comparison to really fast moving objects in sport like shuttlecocks, for example. And we want to illustrate that air resistance. Now a key thing, think about the point of application point I made earlier. Air resistance acts on the entire body, or at least its frontal cross-sectional area. So we have to illustrate it illustratively. Okay, and we do that by doing it from the centre of mass. Now I'm going to say that she's got that kind of air resistance. Air resistance, okay? Air resistance. And I'm going to illustrate that with AR, air resistance. Okay, so we've got this degree of air resistance, or you could call it drag in water, for example. Sometimes we even call air resistance drag. Now what I want to do, remembering that we're trying to illustrate a state of inertia, is ask you then, where would you illustrate the friction arrow, and in which direction and which length? Those three principles. From where, in which direction, and to what magnitude. I'm just going to pause for 5 seconds, or at least not say anything for 5 seconds. I might even scratch my nose to treat myself. You guys have got 5 seconds to put it in. I actually went to scratch my ear, took my headphones off, and they fell off. So I was a bit longer than 5 seconds. Never mind. So what did you come up with it as an answer? And can I just give a health warning? If you guys are on the AQA exam board, I'm going to just give you guys a bit more information in a second, because there is one other piece of information out there in the ether that suggests that AQA could present this slightly differently, and I'll cover that just in a second. So don't worry, I'm going to cover that as well. Okay. So the key thing with friction, guys. The key thing with friction that I would tell you is that it's what we'd call the anti-slipping force. The anti-slipping force. Now, the way it works is that whatever direction between the two contact points, the two surfaces, whichever direction the performer has a tendency to slip in, friction will oppose that force. So at the moment, this performer, she is driving her foot backwards. She's gripping that ground with the underneath of the sole of her trainer, and she's gripping the ground and pushing backwards. So her tendency to slip at this point, at least, is in that direction. Okay, would you agree with me? She's pushing in this direction. So the tendency for her to imagine her slipping as if it was ice, for example. Her foot would potentially slip in that direction. So therefore, we would always have the contact point as the origin. We now have a friction force arrow, which is illustrated like this. Okay, friction force arrow, which is illustrated like this. Now, what I would like to quickly say to you is that in my illustration, weight equals ground reaction force, so we've got zero net force there, and we've got air resistance equals friction in terms of their magnitude. They're opposite in direction in each case, of course. So what does that cause? It causes a state of inertia and constant velocity. But James, you said she's going in that direction. Well, yes, it's because the acceleration happened before this point. Okay, so now she's still moving in that direction in a state of constant linear momentum. If we look at the entire body, excuse me, and she's moving with constant velocity. It's like her race speed, I suppose. You know, if she was fatiguing at the end or doing a sprint finish, or she was going uphill and slowing down, for example, you know, we'd have the friction less in that case. Well, it would, you've got to bear in mind the hill example is a slightly difficult one because the weight would actually end up acting down towards the centre of the earth in a different direction. Anyway, let's not get into that. But the point is, we have got this performer acting with constant velocity. Now, you AQA dudes out there, just one thing I want to state here: when this performer's foot first hits the ground, you can make an argument that so this is during the foot strike specifically, not in the drive phase, which is what we just looked at. You could make an argument that her foot could potentially slip in that direction. Okay, and we have one illustration from AQA which has shown that they have used friction as the anti-slipping force, and that it acts backwards in that direction. And I would just ask you to be aware of it. I'm aware of it. I'm pretty confident that this is the format that you would potentially be asked a question, okay? But I'm just mentioning it. I've actually had AQA formally respond to this, and this is how they explain it. When the foot first strikes the ground, the tendency for slipping is forward, so the friction acts back. But once you're driving and pushing back with the foot, of course, the friction acts exactly as I've just illustrated it, forwards. So the skill I'd like you guys to really develop is to represent the overall movement with this combination of vectors, and I think we've done that quite neatly. Okay, we're going to assume that this guy is accelerating. All right, so again, we've got now direction of movement over there. I'm going to go through this one fast. Okay, in fact, I'm just going to sketch it. Direction of movement is over in that direction, and we are going to suggest that he is accelerating. All right, so that's what I want to say. Perhaps the questions ask me, illustrate all the forces acting on this performer in the first 20 meters of a 200 meters. Well, first 20 meters, they're accelerating, right? So ever so quick, I'm sketching. I'm not even doing straight lines. Look, I've got my weight force. I have my ground reaction force, which is opposite in direction but equal in magnitude. The green and the purple should be opposite and equal. Okay, he's accelerating, so it's early in the race. Well, perhaps his air resistance is only small. Okay, so there's his air resistance. It's only small because he's not going fast yet. Remember, we looked at factors affecting air resistance in our last session. But we have his friction is big. Okay, so what does that show us? It shows us acceleration in that direction. Why? Because friction is greater than air resistance. Are you guys happy with that? Does that make sense to you? Remember the key things: direction of movement. We've got all of our vectors being illustrated. We've got the relative magnitude of those vectors. We've got, and guys, can I just stress to you, please make your application points for each vector correct. If I do the weight force, and I don't know, I do it here, here's weight force, it's just wrong because this point of application is wrong. Okay, if the friction comes from anywhere apart from the contact point between the floor and the foot, it's wrong. Or it might not be a foot, it could be the bottom of a ski, I suppose, something like that. If air resistance doesn't come from the centre of mass, it's wrong. Okay, get it right. And ground reaction force exactly the same as I said with friction, but of course vertical. So this would illustrate someone accelerating. Now, I'm simply going to ask you, again, I'll just take 10 seconds. If you had exactly the same image, perhaps of a fatiguing performer, how would you show deceleration? Just think that through. If you're with other people, just quickly chat it through. I'm not going to demonstrate it. Just give you 10 seconds. How would you do that? So I'm assuming you've kind of thought that through a little bit. And of course, the idea, if this was a decelerating body, you know, if we had decelerating, if we had decelerating, what we'd have to have is the air resistance would have to be greater than the friction. And this could be sort of, you know, at the end of a race or just after they cross the finish line or something like that, where effectively they stop kind of pushing along the ground so that the friction goes down. okay, and the air resistance, they're still travelling fast at this point, increases. Okay, so in this case, they would slow down in that way. You could make an argument for that sort of opposite friction arrow. They put the brakes on effectively. It's a nice way to think about it, actually. All right, let's do a question. So, Josh wants to compare his own performance with that of Usain Bolt. Not a good idea in my opinion. Illustrate all the forces acting on Bolt in the final 10 meters of a 100-meter sprint. Now, this is really interesting. The final 10 meters of a 100-meter sprint. My question to you is, what state of motion do you think is happening there? But here are your choices. Do you think that Bolt is accelerating in the last 10 meters? Do you think he is at constant velocity in that last 10 meters? Or do you think that he is decelerating in that last 10 meters? And my point to you would be, no matter which one of those you chose, you should be able to correctly label this graph, this illustration, or vector illustrate this drawing. Now, for me, he's not going to be accelerating in the last 10 meters, so let's get rid of that. Our choice comes between constant velocity and decelerating. Now, Bolt is an elite sprinter, the elite sprinter, at least he was until last year. And he's doing 100 meters, not 200 or 400. So in my opinion, this is a constant velocity example. Okay. Now, if this was at the end of a 200 meters, I would probably put it as decelerating. If this was the end of 400 meters, I'd definitely put it as decelerating. But I'm going to give him the benefit of the doubt. Now, I would hope that the exam board here and the examiners would give you credit for both of these as long as you correctly illustrated it and described it. I think I've got my answers in. Let me get rid of those. So let's have a quick go at it. So what have we got? We've got weight force acting down. There's our weight force. We've got ground reaction force acting up. So he's accelerating neither upwards or downwards. So there's my ground reaction. So 0 net vertical forces. There's my GRF. Now we've got his air resistance, which comes from here. He's a pretty fast guy, so I'm going to make this quite long. There's my air resistance. And I'm going to make his friction exactly opposite and exactly equal to that. So I'm going to go for friction from here. And I'm going to go for friction at the same length. You guys would measure, as I said before. So for me, that illustrates constant velocity. Now, what have I missed, folks? What's the crucial thing I've missed from my illustration? What is missing? And I hope you're telling me it's a direction of movement arrow. Okay, so that question, I think, is a really fascinating one. That's how we want to illustrate that. Again, I just make the same point for you AQA guys. Don't be shocked if you get given a drawing and you've got a friction back arrow, because what they're illustrating there is that as the foot strikes the floor, the initial potential for slipping is forwards, so therefore friction is backwards. I don't think they'll give you that, because I think they've realised that they've confused people, I hope. But just have an awareness of it. Okay. Let's move down. Making reference to Newton's second law, describe the motion that you have illustrated in the previous section. So we've got exactly the same question as we had earlier for the vertical forces. Let's have a look. The athlete is in a state of constant velocity, so I'm justifying my 0 net force, which is characterized by 0 net force. Acting. Friction equals air resistance and weight equals ground reaction force. And that is basically my 3 marks for my max. This can also be considered to be terminal velocity. Terminal velocity means top speed, by the way. It's a nice term for you to learn. But I could go further with my answer and say an increase. So I'm saying what would happen if something changed. An increase in friction would cause an acceleration. And after the line, so after he's finished, a decrease of friction would cause deceleration, okay, because of course air resistance would be greater than friction. So, but I've already got my max up there, and we've done well. I should have said, this one here, you probably find that this is a 3 to 4 mark question for the drawing itself. Okay, so what do we get? 1 for the direction of movement, we get 1 for the relationship between ground reaction force and air resistance, 1 for the relationship between friction and weight, and we get 1 extra one that the point of application was correct in all circumstances. And there's my max. Okay, so that's the skill we want you guys to develop. I am slightly worried about that AQA thing. let's see what they put in let's see what they put in on that exam. A lot of people have been in touch with the exam board, so I'm assuming they've picked up on there's some concerns around that, and I'm sure you'll get a consistent question if this topic comes up. Okay,